This is the third lecture on deadlock. In this lecture, we'll look at how to deal with deadlocks. The learning objectives for this unit are to first identify which deadlock condition is prevented by using a specific prevention mechanism, and second, learn how to modify the resource allocation mechanisms in a piece of code to prevent deadlock. So one way to deal with deadlocks is to just pretend that deadlocks will never occur. For example, an ostrich sticking its head in the ground. This basically says you write your code, you run it, most of the time it works, and occasionally it deadlocks and you just reboot the system. This is a surprisingly common approach, and it works okay for code that's not very important and where the deadlocks don't occur very often. However, within operating systems, this is a very bad approach because your operating system will be less reliable and people will stop using it. Another thing you can do is you can detect when a deadlock exists and then try to respond. So how might you discover if a deadlock happened? Well, periodically check to see if your threads are stopped running, if they're all waiting. A simple way to do this is with timeouts, and many systems, such as databases and operating systems, have a timeout that says if a thread waits more than a minute to acquire a lock, probably there's deadlock and we should do something about it. So now that we know there's a deadlock, the question is, what can you do? Well, one thing that can be done that happens in many operating system kernels is to basically crash the system. You might have seen the blue screen of death on Windows, and this can happen when the deadlock occurs. The recovery here is to basically reboot the system and restart whatever program you were running. It's not a very nice way to recover, but it does work. Another option is to pick a thread and terminate the thread. For example, the lowest priority thread or the thread that's been holding a lock waiting the longest. This is only possible in certain kinds of applications because many applications, when you terminate a thread, will cause it to corrupt data and leave the system unworking. The problem really is that the thread has to clean up when you terminate it because it's already holding one lock and it may have modified the state. When this works, threads have code that know how to clean up when they're terminated, and they usually retry from scratch. The reason this works is we've broken the non-preemption condition for deadlocks because now we're allowed to preempt a thread that's holding a lock, force it to give up the lock, and let it retry. And as mentioned before, this is often done in database systems when they discover deadlock despite the drawbacks of making threads having to clean things up. This works in databases because they know exactly what a thread is doing in terms of what data, part of the data it's modifying. There are other more proactive ways of dealing with deadlock. This means that we can modify our code or write our code in specific ways to prevent deadlock from happening. Now it turns out that there's no single approach that is appropriate or works in all possible circumstances. Instead, you have to think about what do I need in a particular circumstance and find a technique for the given circumstance that prevents one of the four conditions of deadlock. So one possibility to solve this is to say, well, we'll stop deadlock by having no mutual exclusion. You might say this is crazy, but we need locks. But the real solution here is make resources shareable. Suppose, for example, we have a set of files and we don't really need to write them. Instead, if we make files read-only, then there's no need for locks anymore because we don't need to have them be locked with mutual exclusion. A second possibility is to take a global variable, and instead of having a single global variable that is written, we're going to have per thread variables where we don't need mutual exclusion anymore. Suppose instead of a global counter of something, we have a counter for each thread. Now we don't need mutual exclusion and there's no more deadlock possible. However, this isn't possible in all pieces of code. What we'll now do is look at the example code we saw in the last lecture and see how we can fix it. So in this code, thread 1 locks X and Y, thread 2 locks Y and X, and because we're using locks and the threads acquired the locks in different orders, we can have deadlock. Another way to solve this is to prevent hold and wait. Hold and wait happens when you acquire one lock or one resource and then try to acquire another resource before releasing it. In this case, the solution would be to release all locks before acquiring the next lock. So thread 1 here would lock X, and then unlocking Y would re-lock X. Thread 2 would do the same thing. This prevents deadlock because there's no time when the thread is holding a lock and trying to acquire a second lock. This works in many cases. However, if you have some requirement about the relationship between A and B, you might want to lock both at the same time, and no hold and wait doesn't allow you to do that. Another way to prevent hold and wait is to have a single lock that covers both things in this particular circumstance. So instead of having locks X and Y that protect A and B, we can have lock Z that covers both A and B. In this case, we just acquire a single lock that protects everything, and we don't have to acquire multiple locks, and wait while holding a lock. The problem with this approach is that it has low concurrency because now all threads accessing A or B, even if they don't access both, acquiring the same lock and can't run at the same time. So no hold and wait can be handled by either releasing locks before acquiring a new lock or by having fewer locks called lock coarsening. And the problem is low concurrency. A third possibility is to allow preemption. Well, typically locks can't be preempted, but in other kinds of resources we might be able to support preemption. Suppose thread A is waiting for a resource held by thread B. Well, can we take the resource away from B and give it to A? One way to do this with memory is to use virtual memory. Take the memory that B has allocated, swap it out to disk, and then give the DRAM back give it to A. This is one way to add preemption to a system. However, it doesn't work for all resources. It works for some resources where you can completely save the state some other place, like CPU and memory, but you can't really use it if you can't save and restore the state, because otherwise taking it away causes correctness problems. This is particularly the case with locks. So a final way to solve deadlock is to prevent circular waits. A way to do this with locks is to impose an ordering on all resources. So what we say is we'll take all the locks in our system, we'll give them a ranking, and you must acquire the highest ranked lock first. In our case, we might say lock X is ranked higher than lock Y, so all threads must lock X before they lock Y. In our example here, what we will see is that both threads are locking the things they used to before, but now they'll always lock in the same order, so there's no circular wait and no deadlock is possible. This gets difficult, however, when we don't necessarily know locks we're acquiring are in advance. Remember the transfer code we had here for transferring money from one account to another? The things that we lock, account 1 and account 2, are variables. If we just take code that always acquires the lock on account 1 before lock on account 2, how do we make sure that it respects the global order? We'd have to add additional code to actually test which lock comes first and then acquire them in the right order. So this could work, but it would require extra code to check which lock comes first. This gets even worse when we're dynamically choosing which locks to acquire. Look at this variation of the transaction code, which takes 3 accounts. In this case, we actually look at the balance of account 1 and account 2, and based on the relative balances, we might either move the money to account 3 in the first if clause, or to account 2 in the else clause. In this case, we don't know if we need to acquire a lock in account 3 until we've looked at account 2. So how do we order the locks in this case? In this case, if account 3 was the highest priority lock in the global order, we'd have to always acquire account 3 before account 1 and account 2, which would make the code even more ugly and would have less concurrency because we need to acquire more locks. The takeaway from this is really that deadlock is a complicated problem. There's many solutions to solving it, but not all of them work in every situation. This is the end of Deadlock Unit 3. Please take the quiz before attending class.